Hello and welcome to this lecture series on microprocessor and microcontroller. And this is video number 20, and we are studying 8086 microprocessor, right? So in this particular video, we are going to address a very short topic which is called as memory organization in 8086. So we will see that the externally interfaced memory, which is of 1 megabyte, is not used as a single chip. Rather, it is used as a combination of two chips of size half MB each, and they are organized into odd and even memory banks. So we will see what these even and odd banks are, how they are accessed, how the address and data buses are connected, and when these signals are activated or deactivated. I mean, odd and even memory bank, it is not essential for them to be on for every time. Both of them are not on every time. Sometimes odd will be on, sometimes even will be on, and sometimes both of them might be on. So we will see all those issues, but the primary advantage of using odd and even memory banks is since 8086 is a 16-bit microprocessor, and if we want to write a word that is a 16-bit data inside the memory location, then definitely we have to access two consecutive memory locations because every memory location is of 1 byte only. So if you want to write 2 bytes in one machine cycle, then this odd even memory bank segregation will help us. So that's what this video is all about. So let me just quickly take you to the slides. Yeah, so here let me first show you what we have already studied about this. We have already seen this table when we were studying the beginning lectures of architecture and pin diagram. So here you see if your A naught is 0 and BHE bar is 0, right? So in that case, whole word from and to even address will be transferred, right? So what does this mean is since the externally interfaced memory that you see here, this externally interfaced memory, every location that you see is of 1 byte, right? Every location is of 1 byte. So in this externally interfaced memory, if you want to write one word, then that will simply mean that you have got 2 bytes to write. So definitely two consecutive location have to be written, and if they were to be written in one machine cycle, that means at once they have to be written, then we use this combination. A naught will be equal to 0, in which case we will see that the even memory bank will be active and BHE bar will also be equal to 0. If BHE bar is equal to 0, that means BHE is equal to 1, and that means that odd memory bank will be activated. So we will see how these two are activated in a short while, but this is the table that we have already studied. Similarly, if you just want to transfer the data at upper byte from and to odd address, then in that case A naught will be 1. That means A naught will be deactivated. So we will see how A naught is 1 and it is deactivated. Actually, this will be connected to the chip select of this particular bank, and here you can see that this chip select is through this bubble symbol, where we mean that whatever signal is applied here, it is inverted. So this bank can be activated when and only when A naught is equal to 0. So if A naught is equal to 0, in that case this acts like a NOT gate, and one signal will be transmitted inside this memory, so this memory will become activated. And similarly, this bubble symbol also operates for BHE bar. So when BHE bar signal is 0, since it is an active low signal, so we will say that this has been activated, but this 0 signal will be transmitted as 1 here. So in that way, this memory will become active. So this bubble here means it's a NOT gate. So when A naught is 0, this bank will be activated, and when BHE bar is 0, this BHE signal is activated. So in that case, this memory bank will become active, right? So if you want to transfer upper byte from and to odd address, then we will be using this combination. BHE bar will be 0, that means odd bank will be selected, and A naught will be equal to 1, which means that this bank will not be selected. Similarly, 1 0 for lower byte from and to even address, and 1 1, that means none of them will be activated, because if you will apply 1 here, this will be deactivated, and if this is 1 here, this will be deactivated, right? So that's what we are going to verify today. But let's not begin with this big example. Let me take a smaller example, and the smaller example is actually this. So assume here that we have this kind of memory, right? So first have a look at this particular side, then we will come to this side. So this is, what is this? These are addresses of memory locations, right? Every memory location is 1 byte, that is 8 bits. So the address of first location is 0000, second is 0001, and so on and so forth. We have got total 16 locations. So addresses, they begin from 0000 and they end at 15. So a total of 16 memory locations are there, and addresses can be accommodated because of that in only 4 bits, right? So this is one way we can buy this kind of chip from the market, and this kind of chip can be used for our processor. Not our processor, because our processor will require 1 megabyte of memory. So here we only have 16 memory locations. Our processor will require 1 megabyte, that is 2 raised to the power of 20 such memory locations. That means 20 address bits will be there. However, this is a pilot example, so we are just taking only 16-bit addressable, 4-bit addressable memory. It is a total of 16 locations will be there, and each location is 1 byte. Now, uh, an alternative way of having the same kind of memory is, you can have two chips. You can have two chips, and each of the chip has only 8 addresses, right? 8 addresses. So total of 16 addresses will be there if you combine both of these chips. So in case inside the market this complete memory is not available which has got 16 addresses, so you can buy two RAM chips or two ROM chips which are having 8 address locations, and you can combine both of them. Now, this is not the primary reason why we use this even and odd banks, right? The primary reason I will make it clear a little bit later, but let us say that instead of using this single chip, we are using a combination of two chips, right? And how is the combination being used? Let us say, since we want to have finally the addresses of 4 bits only, because ultimately by using these two chips we are trying to imitate these 4 bits, right? So let me keep all the even addresses shown in yellow in one chip, and all the odd addresses shown in another chip, which are shown in green color here, right? So 0 to 468 etc will belong to this chip, and in 4 bits, so this is not a part of the memory, but I have just drawn it to illustrate you, right? The memory is only this. These are the 3-bit addresses, and these are the 1 byte locations. Similarly here, these are the 3-bit addresses, and these are the 1 byte locations. But for the purposes of illustrations, I have just transferred these yellow addresses in one chip and these green addresses in another chip, right? So that we can see that all the even addresses belong to one bank and all the odd addresses belong to other bank. So that is how they are named as even bank and odd bank, right? So uh, however, their actual physical addresses, you can see they are of 3 bits and they are exactly the same. Now, uh, what we are now going to do is, we are, if you see the similarity 0001, 0011, so if you see the first 3 bits, if you see the first 3 bits, first most significant 3 bits, they are as good as the address of this chip. So if you notice any entry, suppose 1001 here, so the first 3 bits are 100, and 100 is the address of this. So in the odd memory bank, these first 3 bits, or the first 3 most significant bits, they are as good as the address bits. And this is true for even bank also. If you see the first 3 bits, 001 here, this is 001. So this is also true for this particular case. So whether it is odd bank or even bank, the first three bits are as good as the address bits of this chip. Note that the addresses of this are in order. I mean 0, 1, 2, 3, 4, 5, 6, 7. And similarly here also 0, 1, 2, 3, 4, 5, 6, 7. Which is very obvious because whenever you buy a memory from the market, it will have addresses in their regular order, right? But by segregating this into even and odd banks, we have got one very good thing, that if you leave the last bit in either even or odd bank, the first 3 bits, they are as good as the address bits. Now let us utilize this to our advantage. Now this last bit that you see here, which is 0 for every case in even bank, let us use it as an activation signal to this particular chip. So obviously, when a number is even, its binary equivalent will have the least significant bit as 0, right? So this is even bank. So this will be activated whenever A0 is equal to 0, right? And that's what we saw in table also. In this table also, whenever A0 is 0, then the corresponding bank was activated, because if A0 is 0, in this case we were transferring the whole word, and if A0 is 0 here, we were transferring the lower byte from n to even address, right? So this is what we have seen in this case also. So whenever A0 is 0, because of this NOT gate, this IC will become, this memory will become activated, and that's what we want. So this is A0, right? Similarly, if you see here, here is a 1. So whenever A0 will be equal to 1, we could have used that signal as an activation signal here, but instead of that, we are using this BHE bar signal. So I will come to the logic of this in a short while, but this BHE bar signal, it is called as bus high enable, right? Because addresses, they begin from 0000. So even is considered, and we have considered this as the even bank. So obviously this is, and if we use little endian storage format, then if you want to store say 2 bytes here, 2 bytes, suppose you have a content of AX register which is divided into this A higher and A lower. So obviously the higher order byte will contain higher order thing. That means 0001 will have the content of AH, and 000 will have a content of AL. So in that order, I mean, this odd memory bank can be considered as higher order memory bank. So this is BHE, bus high enable bar. So that is why it is called as bus high enable signal, right? Because odd memory bank is higher as compared to the even addresses, because addresses begin from the even side. If we consider 0 as the even address, then addresses begin from the even side, and because of this little endian format, we have got this thing. This is the even bank is the lower order bank, and odd bank is the higher order bank. And odd bank is not activated when A0 is equal to 1. Obviously it will be activated, obviously it can be activated when A0 is equal to 1, because if you see, the last bit is 1, but there is a purpose for this BHE bar, which we are going to discuss soon, right? So I think the activation thing is all clear to us. Now the next thing is, to the even order bank, we will connect only the lower byte of the data bus, that is D0 to D7, and to the odd order bank or to the higher order bank, we will connect the higher order data bus, that is D8 to D15, right? For the obvious reasons, because we are using little endian format. So if we want to keep the content of AX register, which is a 2 byte register, onto location 0000 and 0001, so 0001 will contain A higher and 000 will contain A lower. So obviously lower order content will be kept on lower order data bus, and since lower order data bus is used with these yellow things, so D0 to D7 will be applied to this particular chip, and D8 to D15 will be applied to this particular chip. So now, whenever you buy a memory from the market, it only has pins for address lines as well as data lines. So you have to connect some data lines into the data pins and address lines into the address pins, right? So that is what we are going to do here. Now, after that, let us come to the main point, right? Let us come to the main point. Suppose now in this slide, if you see that we want to write a whole word from and to even address, right? So since we are going to write a whole word, that means a 2 byte data, so it will begin from even address, and it will also consume the next odd location, because 2 bytes will be there in even and odd address. So definitely the value of A0 has to be 0, and the value of BHE bar has to be 0 for both of the banks to be activated, right? So, and the complete data bus will be used from D0 to D15, because we need to have 2 bytes. So now in this particular case, if you see here, A0 will be 0, BHE bar will be 0, both of the memory chips will be activated. So suppose we are trying to write something at an even address. Let us say we want to begin from 0100, and the next location is 0101. That means fourth and fifth location we want to write. So obviously we have applied A0 and BHE bar as per their table, and this, since we are seeing the first three bits 0 1 0 in this A1 A2 A3, since A0 has been attached as an activator signal, so A1 A2 A3, here also A1 A2 A3. So if you see the first three bits of both the numbers, they are 0 1 0 and 0 1 0. So in this bank also, this 0 1 0. So let's see where this 0 1 0 is. This is the 0 1 0, which corresponds to 4. And here also, because of this A1, A2, and A3, 0 1 0 will be seen. So this fifth location will be seen. So if both of them are activated, that means the data from both of the buses will be copied to these locations, location number 4 and location number 5, in just one machine cycle. So I'm underlining this complete sentence. You will be able to transfer the data on the complete data bus, that is D0 to D7 and D8 to D15, if both of these signals are activated and you have selected the 0 1 0 and 0 1 0. So location number 4 and 5 are simultaneously selected. So you see here an even location and an odd location has been simultaneously selected by these two signals, and that is how you will be able to write one complete word, that is complete 2 bytes into location number 4 and location number 5. So first location number 4 will come, it will have lower order address, it will have lower order data, and higher order data will be kept onto the odd bank, right, at the fifth location. So this is how you are able to write a complete word, and that is why we have segregation into odd and even banks. And that is why we do not have A0 as activation signal here, because A0 can either be 1 or 0 at any time. And if we want to activate both of the memories at the same time, that is not possible if you supply A0 as activation to both of the signals. That is why we have got this bus high enable here, right? So let us come to the second part. Let us come to the second part where we have bus high enable as 0. That means your high bus, that is the odd bus, will be activated, and A0 is equal to 1. That means the even order memory will be deactivated. So in this case, what will happen, let us check. So this is deactivated because A0 has become equal to 1. So because of this, it will become 0, and this is deactivated. Now here this thing is 0, that means this thing is activated. So if this thing is activated, obviously the higher order data bus, that is higher order data or the upper byte of the data, will be transferred to the corresponding address, whatever address has been put on A1, A2, and A3. That is why in the table you can see upper byte from and to odd address, right? Similarly, you can verify it for these two also. You will be able to figure out that this segregation into odd and even memory banks have helped us to write a complete word into the memory at once if it is desired. And even if you want to write only one byte into the memory, so you can select either odd bank or even bank by selecting these appropriate signals, right? So this is the advantage of using segregated memory. The another advantage is, so you see here you have used D8 to D15 for this bank and D0 to D7 for this particular bank. Now it would be very difficult, to do so here. Why? Because address lines A0, A1, A2, A3 are connected here, which is fine. But this complete memory chip will have only you know 8 bits for data bus, right? So which one of this should you connect, D0 to D7 or D8 to D15? If you want to make consecutive, if you want to make alternate locations as odd and even, out of this memory chip only 8 bits will be there. So the 16 bit data bus can never be connected here, and since it will be different for alternate locations, so that is not possible. So this is the second advantage of using odd and even memory banks. So this has to be done in 8086. You cannot use this kind of memory there. So odd and even memory bank is not because you have these short chips available in market. It is primarily because you want to write complete word in one machine cycle, and also you want to connect the complete this data bus to both of the chips, right? So this is the advantage of using this odd and even memory banks in 8086. Now this is a pilot example. Let us see it for the bus the memory that we have, complete 1 megabyte memory. So in the even memory bank, you see you have got all even addresses 02468 and so on till the end. And here you have got 13579 till end. And the address lines that you have selected are A1 to A19. Similarly, the same address lines have been used here, but the select signal here is A naught, which is connected through this NOT gate to this chip, and BHE bar, which is again connected here. So now this table will make sense to you in context of this particular diagram, right? So this is what I wanted to discuss about this memory organization of 8086. So this is it for this particular video. I will see you in the next one.